All right, welcome everybody. We're going to go and transfer from mechanical energy into a different type of energy referred to as thermal energy. We'll look at methods of thermal energy transfer or heat transfer, and then we'll also get into some laws of thermodynamics. So the notes that we're going to talk about today in this video cover pages 13 and 14 in your packets. So as I go through some of these videos, some of these slides, I expect you to fill in the blanks as we go along and add any additional notes as needed. So the first thing we're going to talk about is methods of heat transfer. There are three methods of heat transfer that we're going to look at specifically. The first one is referred to as conduction. And conduction is a transfer of energy through the collision of molecules. So all substances, like let's say this metal rod here, are made of metal atoms, tightly compacted together. And as this metal rod is in contact with a heat source, the atoms nearest the tip that are placed directly into the fire become heated up. And as they become heated up, they start to move around a little bit more. And there are a series of collisions that go on within this metal rod, and the more collisions there are, the more energy transfers from the heat source throughout the length of the rod and into the person's hand. So, for example, if you were to take a spoon, a hot spoon, and take it out of the drawer, it would be room temperature. But if you placed it into a pot of boiling water and left it in that boiling pot of water for a series of minutes maybe, and you came back to touch that handle, the handle itself would be hot because the energy has transferred from the end of the spoon that's directly placed in the heat source all the way up to the handle of the spoon. So this method of transfer works best in solids because the particles are closer together. A lot of times solids are more dense. In other words, they're more compacted. Okay, and the focus here is that conduction requires direct contact. Okay, this is very important. In order for conduction to occur, there has to be direct contact. So two objects need to be physically touching each other. An object has to be physically touching a heat source for conduction to take place. The next method of heat transfer that we're going to look at is known as convection. And convection is a transfer of energy through what we call fluids. Now, fluids, you might think, are liquids, and that is true. Okay, fluids pertains to liquids, but it also pertains to gases. Substances where the molecules or the atoms can easily flow over one another are considered fluids. So when we say the term fluids, we're referring to gases and liquids. Convection occurs due to a change in temperature or a difference, difference in temperature, or leading to a difference in the density of the substance. So as an object heats up, as an object becomes hotter, it's gaining energy, and as it gains energy, these molecules move faster, and those molecules start to move faster, they start to spread out, and they become less dense, and they're going to rise to the surface. So if you have hot air in your house, or if anyone has ever lived in a two-story house, you may have noticed that the second story is sometimes warmer or hotter than the first floor because all that hot air has molecules that are moving around very fast, they're spreading out, and they're rising up to the second floor, essentially. As an object, the molecules release energy, they become to cool down or they become cold. And cold fluids, they move slower, they group together, becoming more dense, and eventually they will sink to the bottom. So again, the two-story home, the bottom floor is usually cooler than the second story because all that cold air is more dense. It sinks to the ground level where any hot air is less dense, molecules are more spread apart, they rise to the second floor. Our third method of heat transfer is radiation. And radiation is a transfer by energy through electromagnetic waves, or sometimes referred to as EM waves. So this could be radio waves, ultraviolet, X-rays, gamma rays, all those waves, visible light, transfers all at the same speed. Those are all known as electromagnetic waves. What's unique about these is that this transfer, this method of heat transfer, does not require matter. So what is matter? Well, matter is basically what everything is made of. Electromagnetic waves do not need a substance to travel through. They can travel through solids, liquids, and gases. They can also travel in the voids of space, a vacuum. The more dense or compact the matter is, the slower this energy transfers. So matter actually slows the process down. So the less matter in a substance, the quicker the transfer. Radiant energy can be absorbed or reflected depending on the color. So I'm sure you've been told that black colors tend to be very hot during summer. Lighter colors tend to be slightly cooler. So the lighter the shirt or the lighter your vehicle, whatever, it tends to reflect the most energy. And darker colors like dark blues or grays or even blacks tend to absorb that energy. And if they're absorbing that energy, they're holding in that heat, making them feel hotter. All right, so within our transfer, we've got insulators and we've got conductors. So an insulator is any kind of material that does not let heat flow easily. So the molecules are very far apart in this substance, and it makes it more of a challenge, it makes it difficult for heat to transfer from point A to point B. Things like styrofoam. So sometimes your ice chests will have a layer of styrofoam in them because styrofoam kind of traps energy. It's going to keep drinks cool, and it's going to keep hot drinks hot, and it's not going to transfer the energy from inside to outside very easily. Eventually it will, just not as quickly as other materials. Conductors are materials that do allow heat to flow easily. The molecules are very close together, such as things like metals. So a lot of your cooking equipment is made of metal because you want your pots and pans to heat up very quickly. You don't want to sit and wait hours for your pan or pot to reach 350 degrees. You want it to get hot now. So they're made of metals. Metals have molecules and atoms that are very, very compact and close together, and they transfer that heat energy very, very rapidly. So a lot of times we throw around the word hot and cold, referring to what something feels like, but do we actually know what the words hot or cold mean? Where hot or cold doesn't necessarily describe a temperature, it describes how quickly the thermal energy is exchanged within the environment. So how quickly or slowly that energy is transferred from one object to the next is what we perceive to be hot or cold. Objects feel hot when objects conduct thermal energy into you. Okay? So whenever you touch something and it feels hot, that means energy is being passed from that object into you, into your body, into your fingers. So when you put your hands on your car hood in the middle of summer, your hand's going to feel hot because the energy that car hood has absorbed is being passed into your hand, causing it to feel hot. If something feels cold, that means that the object is having that energy removed. I think removed is a better word here. It removes the excess energy from you. So if you touch your car hood in the middle of January, it might feel cool or maybe cold depending on the weather. because your hand is warmer than the car hood, so the energy from your body is leaving your body and into the hood, making it feel, giving the sensation of being cold. So two objects can have the same temperature but different amounts of thermal energy if they meet two criteria: if they are different sizes, or they're made of different materials. Okay. If you compare an ice cube to an iceberg, okay, they're both frozen solid water. However, one has more thermal energy than the other because they are not the same size. So thermal energy is greater in a larger object such as an an iceberg compared to an ice cube because there's less molecules in that ice cube. All right, so we're going to talk about heat a little bit more. The heat or the thermal energy of the object depends on a couple things. It depends on the temperature. It depends on how much energy is stored in the object's mass, and it depends on conductivity, how well that energy can transfer. Heat is energy, and it's also measured in joules, so we'll express it as simply a capital J as a unit, not to be confused with impulse, which is also a capital J, but that capital J is a variable. This J is a unit, an abbreviation for joules. Heat energy can be positive or negative. So when we're talking about potential energy, kinetic energy, we said it was all positive. There's no direction here. We will refer to positive heat and negative heat referring to whether or not an object is absorbing energy or if it's losing energy. So if an object absorbs energy, we say that it's got positive heat, and if an object loses energy, we say it's got negative heat. Temperature actually describes the speed or the kinetic energy of the molecules in an object. So it's measuring, it's telling us how fast the molecules are moving. Remember, kinetic energy is dependent on velocity. So the faster or the higher the velocity of an object's molecules are, the more kinetic energy it has. The more kinetic energy an object has, the greater its temperature. We'll typically measure temperature in Celsius, Fahrenheit, or Kelvin. So it may be in degrees Celsius, degrees Fahrenheit, or Kelvin. All right, so now we're going to look at the laws of thermodynamics, or the laws of Thermo. We have the zeroth law, and the zeroth law, systems in contact reach equilibrium. For an object to reach equilibrium, we're saying that that object has reached a balance. So one thing to keep in mind is that energy always flows from hot to cold. So if I'm comparing two objects, and one's hot and one's cold, the energy is always going to move from the hot object to the cold object. So if you go touch your car hood in the middle of the summer, in the middle of August, your car hood feels hot. Well, the car hood is much hotter than your body, even though your body is hot as well. Your energy is being absorbed from that car hood because it goes from hot to cold. If you put an ice cube in your hand, the ice cube is going to melt because it's absorbing energy away from your hand. Your hand is hotter than the ice cube, therefore the energy is being released from your body into the ice cube, causing the ice cube to melt. So the energy is going to flow from hot to cold until all matter in both systems reach the same temperature. Okay, that's what we're talking about when we say it reaches an equilibrium. There's going to be a balance, specifically in temperature, of those objects. Okay, another example, if you imagine a window on a cold day, if you touch that glass, it feels cold. If you keep your hand there long enough, the heat energy from your hand will be absorbed into the glass of the window, until the window temperature and the your hand temperature have reached the same are balanced. They are at equilibrium. So no, after a certain period of time, that glass won't feel cold anymore. It feels the same temperature as your hand. Our first law of thermodynamics says that energy cannot be created nor destroyed. It can only be transferred. So what that means is that there has to be some other object that is taking energy away from another object, causing it to be transferred as work. So when energy is lost, or there's a change in energy, then we could say that work is being done. We'll talk more about work in the next unit. So what that means is in order for something to heat up, in order for something to gain energy, something else has to lose energy. There has to be a trade-off. So if I've got object A and object B, and energy is being transferred from A to B, well, A is now losing energy, and B is gaining it. Well, in order for B to gain energy, it had to get energy from somewhere, and it had to come from A. So there's that trade-off. One object is going to gain energy, but at the same time, another object has to lose energy. Okay. When you rub your hands when it's cold outside and you want to heat up your hands, you rub them back and forth vigorously, continuously, and that motion, kinetic energy, and friction converts to heat. Okay, an engine converts thermal energy into kinetic energy. So in your internal combustion engine in your vehicle, you have a series of explosions, small controlled explosions that create heat, and that heat is turned into kinetic energy. In other words, it's turned into moving pistons, moving parts within your energy, allowing your engine to run, allowing your car to move. Our second law of thermodynamics says that molecules have a tendency to become spread out over time. They have a tendency to become disorganized. So if I don't put any energy into a system, it'll become disorganized over time. The word entropy here is a term that we use to describe this. So if I take an ice cube out of the freezer and I put an ice cube on my desk, well, over time, the molecules in an ice cube become more spread apart. There's not as much structure. Ice starts to melt. It forms a puddle of water. Okay? In order to make this or keep this ice cube an ice cube, I have to put in a lot of energy. I have to cool that ice cube down. That means I've got to cool the desk down. I've got to cool the room down. The room has to be the same temperature as the ice cube or colder in order for it to stay the same cube. Without that extra energy, then it leads to disorder, meaning the molecules are all spread apart. There's not a lot of organization. Okay. Another example, if I wasn't in this classroom, if there was no teacher in this classroom for 30 minutes, then there would be students standing up, walking around, not necessarily doing what they're supposed to do. And that would be the expectation. If a teacher walked into the room, the students would be all over the place. There wouldn't be very much order. There wouldn't be very much structure compared to if the teacher was in the room the entire time, giving some instructions, giving feedback, giving directions to the kids that need the directions. Okay, that's what entropy is talking about. So objects with low entropy mean that they are more organized. Okay, there's not a lot of disorder. High entropy means that they're more chaotic, more spread out, the energy's all over the place. And our third law of thermodynamics is the law of absolute zero. So this is really a theory, and it says that it's not possible for an object to have a temperature equal to or less than 0 degrees Kelvin. So absolute zero is 0 degrees Kelvin, and what it says is that at that temperature, molecules would not move or vibrate at all. Now, this has not been proven. necessarily, but if it was an object did reach this temperature, then it's saying that the molecules in that substance would cease to move and they would not vibrate at all. All right, so that's the conclusion of page 14. If you need to go back and look at some things, rewind the video, pause the video, fill in all the notes on pages 13 and 14. These notes are going to help you complete the remaining pages on 15 and 16 and help you answer questions on your test review.